beyond the standard model.
All right, good morning. How are you all doing? Good? Okay, all right, good. Great, yeah, I hope you guys had a great African night last night. I enjoyed sleeping finally after about 2 days. This morning we're going to pick up where we left off last evening, which is talking about, in particular, the motivation for physics beyond the standard model that really does live near the TeV scale, which is this notion of the electroweak hierarchy problem. And hopefully what I either convinced you of or at least gave you some arguments for that you're now thinking about yesterday is that there is a hierarchy problem. It has nothing to do with mystical fears about quadratic divergences. It really is just the sensitivity of scalar degrees of freedom to physics at very short distances, right? And the fact of the matter is, because the standard model is an interacting theory, that the Higgs in the standard model is therefore sensitive to physics in the ultraviolet. Okay, so then the argument that we pursued in the second lecture yesterday was to say, given that sensitivity, if we want to use that as a strategy for solving the hierarchy problem and predicting new physics that somehow is connected to solving the hierarchy problem, there were various ways we could do it. And one of the most convincing, at least given what we currently know, namely that we have a Higgs down at 125 GeV that looks fairly elementary. And then so far at the LHC, we appear to have some sort of mass gap where we haven't really seen anything else beneath the TeV scale. So given those pieces of information, it was suggestive to think that maybe the solution to the hierarchy problem lies in symmetries, right? Maybe there's an extension of the standard model that makes the Higgs mass natural in a technically natural sense when it's taken to 0. And then we sort of argued that really, at the end of the day, in terms of the four-dimensional effective theory, there were really only two options, right? The options were supersymmetry or global symmetries. And there really wasn't anything else available to us, at least in 4 dimensions, to apply as a symmetry that would act on the Higgs mass. So then we sort of talked about the sort of irreducible sets of predictions that came from those ideas, right? Both types of theories predict new partner particles. Those partner particles carry standard model charges, so they're charged under the standard model forces. And then we go look for them. And the details of how we look for them at the LHC depend on the model. But the fact of the matter is we haven't seen anything. And the bounds that we have now at the LHC are pushing past the TeV scale for both classes of scenarios. So it's reasonable to wonder at that point, right, if nature is telling us something. So nature could be telling us that we're just mistaken in general, that maybe the hierarchy problem is not a real problem. That's a possibility that we should remain open to, but it's not obvious that that's really what's going on. But it's certainly telling us that if those symmetry solutions were our solutions to the hierarchy problem, they haven't shown up where all of our normal arguments told us to expect them. So we can do 2 things with that. One is we can give up and work on something else, which you're absolutely welcome to do if that's your conclusion. But the other thing to do is just ask if that really is, if this line of argument that we pursued really is a completely airtight line of argumentation, or if there are other ways that the hierarchy problem might be solved that don't just look like one of these 2 symmetries acting on the Higgs. And that's necessarily a more speculative endeavor. We had 30 or 40 years to actually understand in detail how supersymmetry or global symmetries could protect the Higgs, whereas if you're pushing into new directions, you haven't had nearly as much time to convince yourself of those points. But what I want to do today, at least in this first lecture, is I want us to have a little bit of fun. So I just want to ask the question, if we pushed into different ways of trying to solve the hierarchy problem, what could those possibly look like? What are some directions that you might go down? What sort of qualitative features would those solutions have? The solutions that I'll talk about as I go through the lecture, they'll get increasingly speculative, not particularly well-defined as we get towards the very end. So you shouldn't take these things as somehow canonical ideas that you need to understand all the details of. You should take them as inspiration for different ways of trying to think about the hierarchy problem. And maybe, in the next few years of your career, you can contribute some interesting new ideas to this program. Okay. So again, here's the picture. So I sort of tried to argue that it's fun to think about the hierarchy problem from the perspective of a cartoon, because that really tells you where all the places are that you could attack it. And again, the issue is just that, if we imagine that the cutoff of quantum gravity is some very high scale, as suggested by the value of the Planck scale, if we imagine that the Higgs lives as an elementary scalar up until that scale, then there's some huge energy hierarchy between those scales and the standard model, and anywhere in between, anywhere between the Planck scale down to the weak scale, of course it's possible and indeed likely that we have additional physical mass scales somewhere in between, and we now know all of those physical mass scales should give a contribution to the Higgs mass. And then of course, if we just end up with the standard model down at low energies and more or less one vacuum in which to set the Higgs mass and the Higgs VEV, then we have this problem that the Higgs mass parameter is not technically natural, and we get a hierarchy problem. Okay. So in particular, we talked about you could lower the cutoff. That would be one way to solve the problem, but then you would have a problem understanding why we don't see more things right at the mass of the Higgs. We understood that if you had multiple extra vacua down here in which the values of the Higgs potential scanned, then maybe that would be a potential explanation. And then finally, what we really focused on in the last lecture yesterday was to think about what happened if there was actually a new symmetry acting on the Higgs VEV. Okay. So now I just want to go through those sort of classes of solutions. So adding a symmetry, scanning over multiple vacua, or lowering the cutoff. And instead of giving you the canonical examples of models or ideas that realize these notions, I want to give you some new ideas. And most of these new ideas are only a few years old, so they're not always necessarily fully worked out. In fact, most of them are not even all entirely right. But they're examples of ways to push yourself in different directions. Okay, so hopefully you'll find some of these inspirational. And I really want to emphasize this lecture you should take. You should feel free to ask lots of questions. You should feel free to be provocative because none of these ideas have been firmly worked out yet, and so there's still a lot of room to think about them. Okay, so let's start with the simplest example. Let's start with the sort of a play on what we talked about last lecture was what if we take seriously the idea that the Higgs mass is rendered technically natural because there's a new symmetry of the theory that is manifest when we take the mass parameter to 0. Okay. So the problem that we ran into last lecture was we sort of saw there were two continuous symmetries that we could apply at the weak scale, right? Supersymmetry or global symmetry. And the problem with both of those was that because they were symmetries that commuted in some sense with the standard model gauge group, right? Supersymmetry charges commute with the standard model symmetry generators, and similarly with the global symmetries. That meant we predicted lots of new particles that were charged under the standard model, and then we go look for them at the LHC and we don't see them, right? That was sort of the problem with the symmetry solution. And it might strike you as being a little unfair to the symmetry solution, right? Because the things that we look for at the LHC, for example, we look for the partners of the top quark, and we look for them using their QCD quantum numbers, right? The fact that they're charged under QCD. But that has nothing to do with how they're solving the hierarchy problem, right? From the low energy effective theory, the partners of the top quark are solving the hierarchy problem because they couple to the Higgs in a way that's like the top quark couples. That has nothing to do with their QCD quantum numbers, right? So it's a little unfair of us to be ruling out these theories using their QCD quantum numbers and not their actual couplings to the Higgs that are related to naturalness. Okay. So this is just a question you can ask yourself. All right, is there any way to play this game again to still have a symmetry that's acting on the Higgs down at low energies, that's making the Higgs mass a technically natural parameter, but that isn't somehow a continuous symmetry that predicts all these new particles that we haven't seen? Okay, so the simplest answer is yes, right? Instead of using a continuous symmetry, you can use a discrete symmetry. Now, that obviously has lots of caveats, and I'll try to tell you some of the caveats in the next few minutes. But the notion is maybe you can use a discrete symmetry to help explain the lightness of the Higgs. And then you can get around all of these problems with the fact that we predict lots of particles that we haven't yet seen. Okay, so the idea of using a discrete symmetry instead of a continuous symmetry to protect the Higgs mass, in the last few years, this has come to be known as neutral naturalness because it's an idea about naturalness, right, about the naturalness of the Higgs mass, but it predicts new degrees of freedom that aren't necessarily charged under the standard model. Okay, and that has to do with the fact that we're trying to use a discrete symmetry. So let me just show you again the cartoon of how this has to work, right? For supersymmetry or global symmetries, we had this picture where there was a symmetry that was a good symmetry in the ultraviolet that was protecting us against corrections from unspecified new physics of high scales. And then, of course, we knew that symmetry had to be broken at some scale because we don't see the new states right degenerate with the standard model. So there were some new mass thresholds that broke the symmetry. And then all the particles associated with the broken symmetry gave finite and calculable corrections to the Higgs mass, right? That was how this worked when we talked about supersymmetry and global symmetry. So now you can just ask yourself, okay, can I play the same game, but instead of having a continuous symmetry in the ultraviolet, or at least at intermediate scales, maybe I can have a discrete symmetry. Maybe the Higgs or the standard model fields are related to other copies by discrete exchange symmetries rather than by continuous symmetry transformation. So then you'd ask, okay, maybe if that's what's going on, maybe I have the discrete symmetry, I still have to have some scale of discrete symmetry breaking because there's no evidence that the Higgs or other standard model particles are exactly degenerate with other states, okay? So there probably should be some scale of soft discrete symmetry breaking. That means there are still new partner particles that are floating around somewhere around the TeV scale. But if it's a discrete symmetry that's relating the standard model to other states, then those other states don't necessarily have to have standard model quantum numbers, right? I can exchange one set of fields with a different set of fields, and if I also exchange their gauge quantum numbers, then that means they can be charged in different ways. Okay. All right, and so then maybe there's a picture where there's the Higgs down at 125 GeV, maybe there's a bit of a mass gap, there's all sorts of new partner particles, but if I'm using a discrete symmetry, they're not charged under the standard model. Okay, that seems like a fun idea, right? Because that would tell you, without bending over backwards, well, this might qualify to you as bending over backwards, but without playing any particular games with your symmetry, you can now understand why the Higgs is light, there's still a symmetry, but you can also understand why you haven't seen anything at the LHC, because the new partner particles that you predict aren't charged under QCD, and so they just aren't produced copiously when you smash protons into each other. Okay. So this seems like a crazy idea, but you can actually make it work. All right, so let me give you the simplest toy model of how this could work so you understand the sense in which this also provides a solution, but also understand its limitations. Okay. So the simplest example is a model known as the twin Higgs. So it was written down by Chaco, Go, and Harnick about 12 years ago now. This makes me feel old because I remember this paper when I was starting out as a graduate student. So what's the idea? So it seems like most of the things in my lecture come down to considering simple global symmetries that are spontaneously broken. So let's consider another version of SUN spontaneous breaking like we considered last lecture. So just consider an SU4 global symmetry, and let's again have it charged just under a single fundamental scalar. So let me call that fundamental scalar capital H. And of course, we can write down a marginal and relevant potential for H. So we can write down a mass term and a quartic. And let's assume the mass term is such that H gets a vacuum expectation value that's non-zero. So as always, we'll call the order parameter for that vacuum expectation value F. Now, of course, again, a fundamental scalar getting a VEV, that's going to spontaneously break SU4 to SU3. And by our Goldstone boson counting, right, that yields 7 Goldstone bosons corresponding to the broken generators. Okay. Now, last lecture, when we were talking about the Higgs as a pseudo-Goldstone, we worked in the sort of nonlinear parameterization of the Goldstones where we got rid of all of the UV degrees of freedom and just wrote down the effective theory of the Goldstones. You could do the same thing here, but it's actually just simpler to think directly about this linear sigma model where we literally just have this fundamental scalar and we study its Goldstones directly. Okay. All right, so far we haven't done anything fancy. We've just broken SU4 to SU3. We've got 7 Goldstone bosons. So let's now try to dress this up and make this a model that could be related to the weak scale. Okay, so to do that, let's just imagine as a toy model, imagine gauging an SU2 cross SU2 subgroup of the SU4, right? So loosely speaking, what that corresponds to is, you take the SU4, you identify 2 SU2 subgroups, and you gauge them by introducing gauge bosons and turning on a gauge coupling and coupling those gauge bosons to currents of the 2 SU2s. That's loosely speaking what we mean by gauging a global symmetry. Okay. You could also think, for example, of the standard model SU2 cross U1 as gauging parts of the global symmetries of the fermions. Okay. All right, so just imagine gauging an SU2 cross SU2 subgroup of the SU4. So in some basis, right, I can take my original scalar H that was a fundamental of the SU4, and I can write it as a little doublet under the first SU2, so let me call that doublet HA, and then a doublet under the second SU2, so let me call that HB. Okay, I can always go to a basis where I can decompose my original fundamental scalar in terms of 2 doublets of the 2 gauged symmetries, okay? And in the back of your head, you should think of maybe the first gauged SU2 as somehow being related to the standard model, maybe the weak gauge group, and this other SU2 is being related to some other sector, okay? All right. So if I've gauged the SU2 cross SU2, right, if I have a scalar whose vacuum expectation value spontaneously breaks SU4 to SU3, unless I play particular games with the alignment of the vacuum expectation value of that scalar, generically that VEV will break actually both of the 2 gauge groups, right? the vacuum expectation value will lie in some direction that's not aligned with either of the SU2 factors. And so that means a general vacuum expectation value for H will live partly in the first doublet and partly in the second doublet. So both of the gauge groups would be spontaneously broken, right? And we know every time we have a spontaneous breaking of a gauge symmetry, we eat some appropriate number of goldstones to become longitudinal modes for the gauge degrees of freedom. Okay, so in this case, I have two SU2 factors. If they're both broken, each one eats 3 goldstones, so I eat 6 goldstones, right? And that means of the 7 original goldstones from breaking SU4 to SU3, I leave 1 goldstone behind, and I have 2 sets of massive gauge bosons. Okay, all right. Now this gauging, right, turning on gauge couplings for the 2 SU2s, that explicitly breaks the SU4, right? Just like last lecture, you know, we made the Higgs a goldstone of SU3. We were very proud of ourselves, and then we realized that standard model Yukawa and gauge couplings explicitly broke the SU3, and they spoiled all of the shift symmetry protections. Okay, same thing happens here, right? If we gauge these 2 SU2s, that explicitly breaks the SU4, and so we can go ahead and we can calculate radiative corrections in this theory. So for example, if I look at, you know, radiative corrections to the doublet of the first SU2 HA, then there are loops of SU2A gauge bosons, right, that give me quadratic divergences, and there's a similar set, so these are proportional to the gauge coupling of the SU2A, and there's the same set of diagrams for HB that are proportional to the SU2B gauge coupling. So those quadratic divergences, those radiative corrections, that just tells you you've broken the symmetry explicitly by having the gauge coupling. If there's extra physics at higher scales that couples to those gauge sectors, then they will give the finite calculable corrections to the Higgs masses HA and HB that are different and large and UV sensitive, right? So this is just a statement that I turn on the gauge couplings. If I want to understand how this theory now has UV sensitivity, I can calculate the quadratic divergence, and I find that I get quadratic divergences, you know, that spoil all of the global symmetry structure. Okay. So where's the magic? Okay. The magic is to say, all right, well, if instead of just gauging SU2A and SU2B with different gauge couplings, what if I make them the same gauge coupling? In other words, what if I impose on my symmetry an extra, what if I impose on my theory an extra discrete symmetry that exchanges SU2A and SU2B and causes, therefore, the gauge couplings of the 2 sectors to be identical? Okay, so if I do that, I still have this UV sensitivity, right? I still have these apparent quadratic divergences. But now, if both the SU2A and SU2B have the same gauge coupling, then all of the quadratic divergences, in other words, all of the UV sensitivity from unspecified new physics, as long as it respects this A and B exchange symmetry, right, it will contribute in the same way. And in particular, that will give us mass terms, right, that don't multiply separately HA and HB, but they multiply the linear combination mod HA squared plus mod HB squared. And that's nice because the way I've written it, right, mod HA squared plus mod HB squared, well, this is just the modulus of my original SU4 fundamental squared, right? So, and the reason I got the radiative corrections proportional to unspecified new physics at short distances, it's now proportional to the modulus of this SU4 fundamental squared. So remember, if I broke the SU4 down to SU3 spontaneously, I got 7 goldstones. 6 of those were going to be eaten by these gauge fields. That was going to leave 1 goldstone behind. So we already know, right, without doing any more details, we know if I have a goldstone of a spontaneously broken global symmetry, that the potential for that goldstone will never be proportional to any invariance of the original symmetry, right? So we saw that last lecture when we wrote down the goldstones of spontaneously broken SU3. The only potential they got is from extra things that explicitly broke the global symmetry. But they don't get any contributions proportional to the original global symmetry invariance. So here, right, if I look at the mass terms that I get, so if I have physics in the ultraviolet that's giving me new contributions to the masses of these scalars, as long as I have this exchange symmetry between A and B, and as long as that new physics respects the exchange symmetry, then it will contribute by the same amount, right, to HA squared and HB squared. And that means in the potential for these fields, those mass contributions will actually be proportional to an SU4 invariant. And so this last little goldstone that wasn't eaten, right, by the gauge groups, this last little goldstone will not get any contribution to its potential proportional to these mass terms. Okay, so this Goldstone, even though it doesn't have a full continuous symmetry, the only thing that's really happening here is a discrete symmetry, right? The last Goldstone is protected against this UV correction. Yes?
Why are you talking only about SU4 symmetry? In fact, the symmetry potential is this.
It truly is SO8. It's a little easier just for explanatory purposes to break it down in this way. Absolutely. It really is SO8, and in fact, if you actually want to apply this to the standard model, you want to make full use of the SO8 symmetry and not just the SU4 symmetry. So it's a good question. But I think for explanatory purposes, it's a little clearer to think about this way. Okay. So the particular thing I need to do here, right now the theory that I've written down, I literally want to enforce a discrete exchange symmetry. So the discrete exchange symmetry requires, at this level, if it's a Z2, it actually requires that the ranks of the two gauge groups be the same, okay? So in this current construction, I really should just think of this as applying to SUN cross SUN. I could embed that, of course, in some larger product group, but then all these arguments would just apply to whatever whatever subgroup respect of the discrete symmetry. There is, well, I can talk about it maybe during the Q&A. There's a whole elaborate generalization of this picture where instead of starting the infrared with the discrete symmetry, you actually start with some large symmetry and then you take orbifold projections of it to get some more elaborate combinations of subgroups and some accidental discrete symmetries. Those actually can give you things like interesting Patti-Salam structures with non-trivial exchange symmetries. But that's way beyond what I want to talk about right now. Okay. I just want to finish working out this toy model. Okay, so again, I mean, hopefully you see where the magic was, right? We had a global symmetry, okay? We explicitly broke it by turning on couplings. Normally, the first, if I just turned on different couplings for the two SU2 factors, I would have completely erased any utility of the global symmetry. But if those two SU2 factors respected a Z2 exchange symmetry, then all of the quantum corrections proportional to physics at higher scales, they organize themselves at the level of a mass term into the invariant of the original symmetry. And really, this is just a statement about mass terms, right? So this certainly would not be true of radiative corrections to the quartic couplings, right? Radiative corrections to the quartic couplings would not respect the SU4 symmetry. Okay, it's really the fact that if I'm just constructing mass terms, I'm constructing those out of the modulus squared of fields. And so with the Z2 exchange symmetry, right, then the mod squared of HA squared and HB squared gives me back an SU4 invariant. Okay. All right, so now hopefully you're getting a sense maybe where we're going, right? How discrete symmetries can still help you in some way, because they can make sure that radiative corrections are proportional to invariance of some larger symmetry, even if that larger symmetry is not completely respected by the theory. But you can also start to guess, this trick is not going to fix arbitrarily all of the issues associated with the hierarchy problem. All it's doing is fixing up mass terms. In particular, other radiative corrections to the theory will not respect the full global symmetry again. So at the end of the day, at 2 loops or 3 loops or 4 loops, I should expect to start getting radiative corrections that correct the mass of the Goldstone. But at least at 1 loop, right, if I'm just trying to push off my solution, the full solution of the hierarchy problem to some higher scale, the Z2 exchange symmetry is good enough to help me with that. Okay, so that was a toy model, right? Now you can see how exchange symmetries might help. So now you can ask yourself, okay, can we do this for the full standard model? So how would that possibly work? The idea, again, is we want to identify the Higgs that we've seen with a Goldstone boson of an approximate global symmetry, but the only real symmetry of the theory is some discrete exchange symmetry. Okay, so to apply this not just to the SU2 parts of the standard model, but to all of the couplings, we would need to promote the symmetry to an exchange symmetry that exchanges our standard model with some other standard model. So let's call our standard model A, let's call the other standard model B, and let's call the Z2 symmetry an exchange symmetry that exchanges all of the field labels in standard model A with the field labels in standard model B. So, this idea, of course, has a much longer history that vastly predates solutions to the hierarchy problem. So many people have often thought about mirror copies of the standard model, maybe for reasons of restoring sort of global parity in extensions of the standard model. But in this case, the idea is we're really introducing a mirror copy of the standard model to try to help understand the lightness of the Higgs. Okay, so the arguments about quantum corrections, they work in the same way, right? So now in the standard model, we already know if we at least want to parameterize UV sensitivity, the quadratic divergence doesn't mean anything, but now we know it's a good stand-in for unspecified new physics at high energies. So we can compute the quadratic divergence in the standard model, right? So that gave us the normal set of corrections to the standard model Higgs doublet. And now there's also, of course, the same set of corrections to the doublet of standard model B, right? And because the exchange symmetry relates all the couplings, those radiative corrections are all the same, right? So now we get what looks like a quadratic divergence, the normal quadratic divergence for the standard model like Higgs doublet, same quadratic divergence for the Higgs doublet in standard model B. And so lo and behold, right, everything is multiplying, again, what looks like not two separate invariants of two separate SU2s, but in fact something that looks like an invariant of an accidental SU4. Okay, so now you're starting to see the sense in which this might start to help with the standard model hierarchy problem. All right, so we imagine there's some potential for these that causes them, you know, there's some VEV for HA squared, some VEV for HB squared. We'll call the combined VEV F. So that's the order parameter for breaking the accidental SU4. All right, and again, generically, that Higgs is both of the electroweak gauge groups of our standard model and the mirror copy of the standard model. Okay, so the counting of goldstones is the same as in the toy model that we worked out. So 3 goldstones are eaten to make the SU2A gauge bosons. Well, it's really the broken part of the SU2A times U1 hypercharge A. And the same thing happens in the twin sector. And then we get 1 goldstone left over. So that goldstone, you know, in the electroweak symmetry broken phase, we want to identify with the real standard model like Higgs. Okay. All right, in addition to that, of course, you know, if we just have this linear sigma model, the goldstone mode is the one we want to identify with the Higgs. There's also a radial mode, right, corresponding to the SU4 breaking. So the radial mode has its mass around F, bless you. And so that thing we want to associate. So there's some extra scalar whose mass scale is around the scale F. Now, there's lots of little subtleties here that I've sort of suppressed. So you can ask yourself, okay, so most of the scalar degrees of freedom get eaten to make the gauge fields massive. There's 1 radial mode and there's a goldstone mode. Now you can ask yourself, okay, what do I expect the masses of these degrees of freedom to be? Now, here we've seen that thanks to the exchange symmetry, the UV corrections to the masses of the 2 doublets arrange themselves in this accidental SU4 symmetric fashion. But to really actually, you know, understand in detail how this is going to work and what the masses are of these extra modes, you need to specify the rest of the potential for these 2 doublets. So generically, okay, so here's the mass term for HA squared and HB squared just coming from radiative corrections. So it has the same form. And we also have to worry about the potential particular quartic terms for these. So in general, I can write down a quartic that respects the full SU4 symmetry. So that would be something that is the form mod HA squared plus mod HB squared, right? So if I have a potential of this form, that was really proportional if I wanted to write it in terms of SU4 invariants, right? This is equal to a quartic times that full SU4 invariant to the 4th. Okay, so this is an SU4 invariant quartic I can write down. But if my fundamental symmetry is only the Z2 symmetry, then I can also write down other quartics that only respect the Z2. So for example, I could write down this quartic. Okay, so the second quartic, right, the second quartic, so because of the Z2, I have to have the same quartic coupling for the 2 doublets, but I don't have to have the cross terms that would give me an SU4 invariant, right? So in principle, if the Z2 is my only real symmetry, I'm allowed to write down all of these sets of quartic interactions. All right. So from the perspective of the goldstone mode, right, the goldstone of the sort of accidental SU4 breaking, if there are terms in the potential of this form, they of course don't contribute to the potential for the goldstone, and therefore they don't give the goldstone a mass. But if there are terms of this form, these of course don't respect the SU4, they only respect the Z2, and so the mass of the goldstone, well, the goldstone can pick up a quartic from these terms, and therefore it can pick up also a mass. So to have the goldstone be light with respect to the scale of accidental SU4 breaking, at the level of this theory, you have to assume for some reason this SU4 symmetric quartic coupling, right, is much larger than these quartic couplings that violate the SU4 but just respect the fundamental symmetry of the Z2. So this is the little dark secret of the twin Higgs models and all of these discrete symmetry arguments is you're using the discrete symmetry to explain why mass corrections from very high scales aren't acting on some light Higgs-like state, but to actually explain why that state is somehow lighter than all of the other states associated with this whole structure, you need to have the SU4 symmetry be somewhat of a good symmetry of the theory, in the sense that there has to be a sort of a large SU4 symmetric quartic that connects the Higgs sector, the multiplets of the two Higgs sectors, and that has to be somewhat larger than the other quartics that you're also perfectly entitled to write down. Okay, so that's a little subtlety, and it's worth, if you want to build a real model, you have to think about why this might end up being true, but I just want to tell you for the interest of full disclosure. Okay, so what is the picture you get? So the picture that you get is, if you do all of these things in the right way, okay, you end up with a Goldstone mode that you can associate with a standard model like Higgs, all right? It's protected against physics, corrections from physics in the ultraviolet from short distances because of this Z2 exchange symmetry, because it's a Goldstone of an accidental SU4. Then there are extra heavy states. There's an extra heavy state associated with the radial mode of this pattern of the accidental SU4 spontaneous breaking. And because the discrete symmetry requires a standard model A to be related to a standard model B by a Z2, what you get at the end of the day is something like the following. So if you range for the vacuum expectation value of HA, so the VEV that breaks the weak gauge group in standard model A, if you range that to be smaller than the overall scale of global symmetry breaking, then what you get is, there's a standard model A, our standard model, that has the weak scale where we see it. And then at a somewhat higher scale, corresponding to the overall scale of global symmetry breaking, there's a standard model B. And because there's an exact Z2 exchange symmetry, right, all the states in standard model B, they have exactly the same masses as standard model states. They're just different by whatever this ratio is of the vacuum expectation values between the two sectors. Okay, so that's it, right? Our standard model, mirror copy of the standard model. We arrange it so that the Goldstone of this pattern of symmetry breaking we can associate with the Higgs that we've seen. And then there's some extra Higgs-like radial mode that's heavy that you could associate with the Higgs-like mode in this copy of the standard model. And the only thing that connects these two sectors, right, the only thing that connects these two sectors is whatever mixing you might have gotten from interaction in terms of this form, right? So the SU4 symmetric quartic, this induces a direct interaction between the Higgs doublets of the two sectors. This is like a version of the Higgs portal, right? And this is the only thing that connects standard model A with standard model B, apart from the exchange symmetry. So the only way these two things talk to each other is through the exchanges of these Higgs states. All right. In particular, everything in the standard model is charged like it is normally, but everything in this other copy, standard model B, is not charged under our gauge group, right? These fields are totally neutral under our standard model. They just charge under their own standard model gauge group. All right. So you can ask, right, just like we did for supersymmetry and global symmetries, okay, how do I understand at the level of the low energy theory, right, in terms of partner particles, how does the cancellation of quadratic divergences work out diagrammatically? How can I prove to myself that I've really gotten rid of this UV sensitivity? So again, you can go ahead and in standard model, in our standard model, right, you can go ahead and take the Higgs, calculate, say, the quadratic divergence coming from top quarks, you get the normal answer. Now you can ask, okay, so there are these new particles that are living in this other copy of the standard model. Those somehow have to be the partner particles in this theory. So how are they coupling to the Higgs in a way that makes the quadratic divergences work out? So I told you the thing that we want to identify with the standard model like Higgs that we've seen, we want to identify that with the Goldstone, the one uneaten Goldstone of this pattern of symmetry breaking. And so what that means is the thing that we identify with the standard model like Higgs that we've seen, it's not exactly the real scalar coming out of the standard model A Higgs doublet. It's a linear combination of the real scalars living in the two Higgs doublets, but because it's a Goldstone, we can sort of write it down in a nonlinear parametrization, right? We can write it down in terms of the Goldstone manifold. And so it mostly lives in the Higgs doublet of standard model A, but it has a small component in the Higgs doublet of standard model B, and the distribution between the two doublets just corresponds to the alignment of the Goldstone on the vacuum manifold. Okay. So the Higgs mostly lives in standard model A, it lives by a small amount in standard model B, and the amount by which it lives in here, is precisely determined by the fact that it's a Goldstone. So if you just take the normal standard model A Yukawa coupling and expand it out, you get this term. If you take the standard model B Yukawa coupling and you expand out the Higgs as a Goldstone, right, you get some funny looking term. But this term you recognize from last lecture when we talked about the Higgs is a goldstone of a spontaneously broken SU3, right, these extra irrelevant operators precisely come from the exponential expansion of the goldstone, okay? So that coupling to the fields in Standard Model B, that gives you diagrams that, again, you recognize from the SU3 example, right? There's some funny irrelevant operator that couples the Higgses to a loop of the top quarks living in Standard Model B, and it's precisely of the form, the sign is given by the goldstone, right? So the sign is flipped relative to this diagram. The couplings are the same thanks to the Z2 symmetry. So it's now this funny looking diagram where the particles running in the loop are the top quarks of the other standard model that cancels the quadratic divergence coming from the standard model. Okay, so these things really are partner particles, right? All of the fermions in Standard Model B are really partner particles. They cancel quadratic divergences just like a normal global symmetry, but because the effective symmetry at low energies is not a full continuous symmetry, it's just a discrete symmetry, these things are no longer charged into the standard model. Okay, so this does a little bit more justice to the idea that if we have new particles related to a symmetry that are helping to protect the Higgs, what really matters is their coupling to the Higgs. It doesn't matter what their other quantum numbers are. And here you're really seeing that borne out. Okay, so this shows you that with a discrete symmetry, you can get new partner particles that are not charged into the standard model. All right, so I think that's pretty cool, right? I don't know if you think it's cool or just terrible, but this tells you, right, all of these historical ideas about how things have to work, you can break them as long as you think in a sufficiently clever way. All right. Okay, so you can tell yourself the same sort of story that we told ourselves with supersymmetry and global symmetries. You can actually ask, what are the really important degrees of freedom for making the solution to the hierarchy problem work? The model I gave you has an exact exchange symmetry that relates the standard model to a mirror copy. So in that version of the theory, you have, for every particle in the standard model, you have a copy in the mirror sector, and its mass is only different by the ratio of the vacuum expectation values. So that predicts a lot of extra stuff in the hidden sector. But turns out you can play games with the symmetry structure. You can make the Z2 only particularly a good symmetry for the sectors of the standard model with the largest couplings. Okay. So you can end up arranging a sort of theory in which there are new partner particles, but the ones that are close to the weak scale are really only the ones, just like in supersymmetry or global symmetries, that are related to the particles that have the largest couplings to the Higgs. All right. These theories have lots of interesting signatures. I actually want to skip over most of it because, well, just in the interest of time, I want to make sure we get to some other crazy ideas. But, well, let me just say briefly, there are lots of interesting things that happen in these theories. So, unlike in supersymmetry or normal global symmetries, we have these new partner particles that are charged into the standard model. So you just make them through their QCD charges. In these theories, right, the new partner particles you predict are not charged into the standard model. So you can't produce them through their strong interactions. The only thing they couple to directly is the Higgs itself. So that turns out, of course, that's very hard, especially if they're heavier than the Higgs. It's very hard to use the Higgs as a way to produce heavy particles, just because the couplings of the Higgs in general are not that large. So it turns out to be very hard to look for these new partner particles directly. That's a very difficult game, and you can see that's a reason why we haven't yet really tested these theories at the LHC. But what is interesting about them is because they have their own, this other sector of particles has its own gauge interactions, it has its own copy of QCD, and its QCD gauge coupling is the same or similar to ours. That means all sorts of interesting things happen in this other sector. So it also undergoes confinement, right? It also has bound states that are baryons and mesons. It has glue balls. These are all very interesting in a rich spectrum of states, not of our QCD, but of someone else's QCD. So that can lead to lots of interesting signatures at the LHC that are very different from the ones that we associate with supersymmetry or global symmetries. Okay, so that's all I want to say about that, but it pushes you in new directions for the signature space of solutions to the hierarchy problem. All right, so now I want to go, so that was taking the idea of symmetries and breaking something about our assumptions, right? That was making the symmetry not a continuous symmetry, but a discrete symmetry. Okay, and we saw at least that pushed us in some new and interesting direction. So now I want to run the argument with the other possible solutions to the standard model, to the hierarchy problem of the standard model. So again, the other possible solutions we talked about were lowering the cutoff or having multiple vacua that somehow you selected between. So let's go back to the selecting a vacuum argument. Again, in my first lecture, or my second lecture, we noted that the popular way to select a vacuum was to imagine there was some sort of anthropic reason, that somehow you ended up with a finely tuned value of the weak scale because any other value of the weak scale would not give you observers. And that is potentially an explanation, but it requires you commit to lots of different vacua existing in some sort of multiverse, and it's hard to know how to make predictions. So you could ask yourself a different question. You could say, well, what if I'm okay with having some potential that has lots of different minima, and in each different minimum, the value of the weak scale maybe changes, but instead of using some mysterious and poorly specified anthropic reasoning, where I need somehow to specify that I get observers only in some vacua and not others, instead of doing that, which is very confusing, let me ask if there's a dynamical mechanism. What if I scan over all of these different minima, and if there's a dynamical mechanism that can cause me to stop in one minimum where the value of the weak scale is close to what we observe. Okay, so that's an interesting idea. I think we've probably all either been falling asleep late at night and wondered if we could do this, or woken up in the morning and thought we could do it. And so there have been some proposals that have appeared in literature recently to do this. The proposals I don't think are fully successful, but they are pointing us in the direction of ideas that we should keep thinking about. So I'm not going to argue to you that these are perfectly successful ideas, but I'm going to argue to you that they're interesting directions that we should think about more. Okay, so these ideas have all been called, after the original proposal, the RELAXION, and I'll try to explain to you why that's a useful name. Okay. So what do we want to do? We want to imagine we have some potential with many different minima over which the value of the Higgs vev scans. And we want to, instead of picking it out by symmetry or by symmetropics, we want to pick it out dynamically. Okay. All right. So there's an old idea about how you could do this, right? Imagine just coupling the Higgs to some field and having the minimum of the potential for that new field be at a point where the Higgs mass squared is 0. So you've been hearing, of course, a lot about axions during your other lectures, and in the axion, you see something similar happens, right? So the axion couples to QCD in such a way that the minimum of the potential for the axion, it sets the CP violating theta parameter to 0, right? So once you hear that, you think, oh, maybe I can do, instead of setting the theta parameter to 0 in the minimum of the axion potential, maybe I can have a sort of similar type of field that couples to the Higgs mass squared, right? And maybe at the minimum of its potential, it sets the Higgs mass squared equal to 0. That's sort of the idea. Okay, so it sounds like a great idea. There's a problem, right, which is how do you make the Higgs mass squared being 0 a special point in the potential of this new particle, right? We already know nothing special happens in the standard model if we take the Higgs mass squared to 0, okay? So how do we somehow make the Higgs mass squared being 0 a special point in the potential of this new particle? Okay. So what's the idea? So the proposal of the original authors of the RELAXION, so Peter Graham, David Kaplan, Surjit Rajendran, this paper is only 2 years old, they said, well, something does happen if I look at the standard model and I imagine I coupled the Higgs to some field that scans over some range of field values. So as it moves over its range of field values, that scans the effective total mass squared of the Higgs. That is to say, if I write the Higgs, if h mod squared, okay, that obviously couples to the mass of the Higgs doublet, and if I couple that to some new field, let's give it a coupling, let's call it G, let's call that field phi, right? Obviously, the total mass squared of the Higgs doublet is whatever the normal to bare mass squared term is in its potential, plus whatever the vacuum expectation value of this field phi is, right? So these two terms give me the Higgs mass, and so if phi is evolving on some potential, if its value is changing, then of course that scans the total mass of the Higgs, right? Okay, so the question they asked is, all right, does something happen in the standard model if I take, forget the Higgs mass squared being equal to 0, let's say I take it from large positive values to large negative values, right? So let's imagine just scanning the mass squared of the Higgs from large positive values to large negative values. So does anything happen? And the answer is yes, right? So if I imagine starting with very large positive value of the Higgs mass squared, and this field is then scanning, and so it plus the bare term goes from some large positive value to some negative value. When it goes from positive to negative, then of course as soon as the total mass squared of the Higgs goes negative, then the potential of the Higgs is away from the origin, and so it gets a vacuum expectation value. In the standard model, of course, when the Higgs gets a vacuum expectation value, that turns on masses for the quarks, right? And turning on masses for the quarks gives a contribution to the cosine potential, to the height of the cosine potential of an axion, right? So hopefully, at least in the lectures that you've had about axions, this is a statement that makes sense to you. The potential for an axion can be proportional to the masses of the quarks. And so in this story, right, now this is sort of an elaborate concatenation of physics, but if you've scanned the Higgs mass squared from positive to negative, when you pass through 0, right, and the Higgs mass just starts to go negative, that turns on quark masses, and that should start to turn on barriers for any axion-like particles that are coupling to your theory. Okay. So the idea that these original authors had, Peter, Surjit, and David had, was what if this particle that's scanning the Higgs mass squared really is itself a QCD axion, right? So what if this is both the QCD axion and has this weird coupling to the Higgs mass squared, okay? Then, if I just look at the potential of this field, let's say I imagine there's some overall tilt to the potential of the field so that it's moving in one direction, all right? As it evolves across its potential, it's changing the Higgs mass squared. At some point, it will evolve across its potential, so the Higgs mass squared goes from positive to negative. The Higgs will get a vacuum expectation value. That's a different direction in the potential field space than anything I've shown you. But when the Higgs gets a vacuum expectation value, that then, through the QCD interactions of this axion, turns on bumps that show up in the potential. Okay, so that's how you make the Higgs mass being 0 a special point in the potential of this field. You use some extra mechanism, in this case related to the contribution of quark masses to the potential for an axion. Okay, so then bumps turn on, and then if you can imagine having a reason why you stop when the bumps turn on, right, then you've ended up in some value, you fix the vacuum expectation value of this field, the total combination of these terms gives the Higgs mass. Even if this were some enormous thing proportional to the Planck scale, right, this field has soaked up most of that and then stopped not far after the point where these two things sum to 0. So the total effective mass squared of the Higgs doublet will be small, and in some sense you've hoped to have solved the hierarchy problem, or at least explained why the Higgs mass that we see is small. But you've done it with dynamics. Okay, that's a pretty cool idea, all right? All right, in detail, how does this work? Okay, again, the idea is we have this field phi, it couples to the Higgs so that when the vacuum expectation value of phi changes, it scans the overall mass squared of the Higgs. We can imagine there's some overall slope in the potential for phi, so that at least it wants to evolve from some field values to other field values, okay? And then we also wanted to imagine that phi also turns out to be the QCD axion, so it has the normal anomalous coupling to the field strength of QCD. And again, the reason for this is we need this coupling so that when the Higgs gets a vacuum expectation value and we turn on quark masses, it'll turn on a cosine potential for the axion, okay? So after, as soon as this total mass squared goes negative and the Higgs gets a VEV, that turns on this cosine potential. But in particular, the cosine potential only gets turned on, loosely speaking, once the total Higgs mass squared goes from positive to negative. Okay. Now, there's a problem with this picture, right, which is if you just, you already know this even before you learn quantum field theory, you just learn classical field theory, right? Or really, even if you just learn classical mechanics, right? If you have a ball rolling down some slope, and it hits some little bumps, it does not care that there are bumps there, right? It has, if it's been rolling down that slope, say, under some gravitational potential for a long time, right, it's been accelerating, it has some enormous velocity, there's some enormous energy density that's involved well, if it's a field, there's some enormous energy density, right? So it's got some enormous energy density stored in its kinetic energy. When it hits these bumps, it doesn't care, right? It just blows through them and keeps on going, okay? So the real problem with this picture, if we just write it down, it sounds good, but if this field has been evolving along its potential, by the time these bumps turn on, it just rolls right over them. It doesn't care. It doesn't stop. Okay. So you need some reason, not just for the bumps to turn on, but then you also need some reason for the field to stop when the bumps turn on. So that means you need a source of dissipation, right? You need to get rid of the kinetic energy stored in this evolving field. Now, dissipation, of course, in quantum field theory, it's a little hard to get nice sources of dissipation, but thankfully we have cosmology, right? So there are ways, if we have fields that are evolving in the early universe, then the conditions in the early universe can end up giving us things that look like effective sources of dissipation in a quantum field theory. So in particular, if I have a scalar field, and I'm just asking what a scalar field is doing during inflation, where the Hubble scale so we have inflation, so Hubble is large. So that contributes a term, if I just look at the classical equations of motion of some field that I'm inputting in an inflating background, there's an extra term in its equations of motion driven by Hubble, and that term, just an analogy with classical mechanics, that term looks like a friction term, right? So inflation provides a source of dissipation for fields that are undergoing evolution during the period of inflation. So the idea of the original authors was, let's imagine all of this is happening during inflation. Okay, so now story runs exactly as we said, only thing extra that's happening is because we have inflation, there's some source of dissipation. That dissipation is draining kinetic energy out of the field, and so then when you hit these bumps, you don't have too much of an energy density, and you can imagine why you stop. All right. So now we get to the details. Now there's lots of terrible, terrible details, right? So lots of things have to happen just right for this story to actually work. This is the classic story of any sort of model building for physics beyond the standard model. You have an idea. For about 30 minutes, you feel like you are the most awesome person in the world, and then you think carefully about all these details, and you feel less good. Okay. Hopefully, at the end of the day, you still feel slightly better than before you had the idea, and then you have an idea. Okay, so what are all the things that have to go right for this idea to make sense? Well, one thing that has to happen is, if this field is going to be combining with some large Higgs mass proportional, say, to the cutoff of the theory, right? And if it's scanning over all of its possible field ranges, including field ranges where this vacuum expectation value is small, so this term is enormous, and values where the sum of these things is approximately 0, that means this field has to scan over some enormous field range, right? If it scanned over a very small field range, and that small field range included the point where these things were 0, that would be a fine tuning, right? You would need to understand why you'd started close to the value of the Higgs mass that you wanted. That would be finely tuned. So you have to have some large field range for phi, and phi has to have enough time to scan over the entire field range to get to the point where it sets the Higgs mass to 0, and it stops. So that actually ends up giving you some parametric constraints that are related to the efficiency of the friction during inflation and how you're scanning over the field. At the end of the day, what it actually tells you is it gives you a constraint on the number of e-foldings of inflation that you have to have while this field is evolving in order to make sure that you evolve through enough of a distance before you stop. Okay. So that gives you some bound on the number of e-foldings of inflation related to the Hubble scale of inflation and related to the strength with which this field couples to the Higgs. So this coupling to the Higgs we imagine is some very small number in order to not create new hierarchy problems from the coupling itself. So that tells you you're going to have a large number of e-foldings. Okay. The next requirement you have, as this field is scanning through its potential, right, it's starting at large values of its potential and going to smaller values. That means the vacuum energy associated with this field is going through some large range. So in order for the friction effects to work and for the dynamics of the field to work in the right way and for inflation to govern the evolution of this field to give us the friction, the vacuum energy during inflation needs to exceed the change in the vacuum energy from moving the field from the top of its potential to the bottom. So that gives you a constraint on Hubble during this inflationary period related to the terms in the potential. Another requirement, right, is during inflation, any light fields are undergoing large excursions that are parametrically related to the Hubble scale during inflation. And so inflation is giving us a source of friction, but we don't want inflation to push the field over the barriers, right? So inflation just has to be just enough to stop us in the right place, but not so much that then it gives our field kicks that go over the barriers. So that requires that Hubble during inflation is smaller than the height of these barriers, so the Hubble scale has to be smaller than lambda QCD. Okay, so you can start to see these constraints are starting to add up, and we'll see where they take us. Okay, there's a fourth requirement, which is that, again, we want inflation just to be a source of dissipation, right? So that slows us down so that we stop somewhere. But of course, we know during inflation, evolving fields undergo fluctuations, not just in their classical direction, so not just down the potential, but in general, inflation also will give us kicks back up the potential. So those are the quantum corrections, the quantum fluctuations of a field in an inflating background. So there's a requirement, therefore, that classical rolling of the field beats quantum fluctuations that kick it back up its potential. And so that gives us one more extra parametric constraint that relates the Hubble scale to the overall mass scale of the theory and the coupling of this field to the Higgs. Okay, so those are lots of constraints, all right? Those are just the things that we can parametrically write down and decide that we need to be worried about. There are other constraints, or there are other considerations that are actually much more dire and much more concerning for the mechanism as a whole. So one of them is that we're imagining that this field that's evolving is an axion-like particle. It couples to QCD like an axion, but actually we're also imagining it couples to the Higgs in this particular way. And that particularly, this coupling, what we imagine, the way it's coupling to the Higgs, that's some non-compact coupling of this axion-like field. So the field, it looks like an axion, like the QCD axion, but it can't actually be uniformly a QCD-like axion with a fully periodic potential. Okay, so really this field that's evolving is not actually a real axion, even if we want to use some of the properties. Model building to make all of that work is very complicated. And then there's something that's even worse or more challenging to understand, which is you also have to understand the cosmological constant in this theory, right? So as this field is scanning through its potential, right? So the field is scanning through its potential, it hits the bumps. We imagine it stops in one of these bumps. Of course, because it's changing over its value of its potential, the minimum of every bump, right, the total cosmological constant is changing by an amount that's large with respect to the cosmological constant that we see in the universe today. So now there's, at the very least, a very surprising coincidence problem, right? We need our field to stop at a place where the total Higgs mass is about what we see. But we also need, coincidentally, the place where that stops, right, to correspond to a vacuum energy that matches the vacuum energy that we see today. In particular, if we end up on a bump to either side, right, these bumps on either side, they only change the Higgs mass by a small amount, so they can't really be differentiated from this one from the perspective of getting the Higgs mass right. But if I go from one bump to an adjacent bump, I'm changing the cosmological constant by an enormous amount with respect to the cosmological constant that we see. So it's very hard to understand, in this theory, yes, you're scanning so that you can try to get the Higgs mass right, but as you move from bump to bump, you're changing the CC by an enormous amount. And so whatever it is you're using to explain the smallness of the cosmological constant, it somehow needs to interface with this whole mechanism in exactly the right way that the cosmological constant comes out right in the bump where you stop. So loosely speaking, what that means is instead of being able to factorize the two problems, why is the cosmological constant so small and why is the Higgs mass small, we normally get to factorize those if we have, say, a symmetry explaining why the Higgs mass is small. In this theory, you have to solve everything at once, and there's much more fine-tuning associated with the cosmological constant than with the Higgs mass. So although it's not perfectly a well-posed question, understanding why both parameters, the CC, the cosmological constant, and the Higgs mass are small is very hard to do in these theories. And the answer is probably all of the winnings that you got in the tuning of the Higgs mass, you lose in the tuning of the cosmological constant. Okay, so those are other problems that should make you pause. But even if you ignored those problems, the 4 constraints that we've just worked out, they tell you what the Hubble scale has to be. It's much lower than the QCD scale. And it tells you that you need the amount of E-foldings of inflation, right, are required for you to go through the full range of this field. And it turns out that numerically you need about 10 gigayears of inflation. Okay, so for this mechanism to explain the Higgs mass, you need as much inflation during this process as the normal non-inflating age of the universe. You may or may not find that problematic, but those are the consequences. Okay, so hopefully what I've communicated to you is it's a really interesting idea, right? We're using the evolution of a field to dynamically select some vacuum in which the Higgs mass is small, even if the contributions to the Higgs mass are large. It turns out all the details of making this idea work are somewhat painful, right? So maybe at the end of the day, this is not how the universe is working, but at least it pushes us in a new direction, right? It opens up the idea of using dynamics to explain the Higgs mass. Okay. There's a final thing. So you've done all this work, right? You have, this very special inflationary sector. You don't worry about the cosmological constant problem. You don't worry about this shift symmetry. You have 10 gigayears of inflation. You think, finally, I got the Higgs mass right? Okay. There's a problem that in this theory, because this field phi couples to QCD field strengths like an axion, right? That means that wherever it stops in its potential also sets a theta angle for the QCD sector, right? So if there's a non-zero vacuum expectation value for this field relative to the periodicity of the theta angle of QCD, that means wherever this field stops, in general, there's some non-zero value of the theta angle. So generically, this field doesn't stop at a point where the theta angle for QCD is also 0. Generically, it stops at a place where it gives you an effective theta angle for QCD that is order 1. Okay, so that's the extra thing that you pay in this theory, is that you predict, because you're using its coupling to QCD to make the bumps in its potential, but wherever it stops isn't necessarily close to where theta in the QCD sector is 0. That means you predict generically a large theta angle. Okay. So you manifest completely the strong CP problem that you've been hearing about in your lectures on axions. So the prediction of this model is not just that you get the Higgs mass to be small, but that the theta angle is order 1. And of course, we know that prediction is off by 10 orders of magnitude. All right. So this model in its original version is dead. All right. Nature told us, even apart from these other issues, strong CP actually kills it. You can play games, of course. Again, what does a model builder do? When they run into some sort of obstruction to their model, they add an extra little epicycle. So you can change this model to make it all work again and make the CP angle 0. A nice way to do it is to say, okay, all we really needed the axion to do was to give us bumps so that we would stop. The problem was, if it's really the QCD axion, it would give us a value for the strong CP angle that was too big. So let's just make it somebody else's copy of QCD, right? That's the model builder's solution. Put the junk in somebody else's sector. Okay. So you can do that, right? For the logic to still work, of course, if this field is scanning the Higgs vev, all right, and you want to use the Higgs, or the Higgs mass squared going from positive to negative to turn on masses for quarks to give you bumps in an axion potential, it has to be the case if you don't make this, if the field is not an axion of QCD, but if it's an axion of some other SUN gauge group, then the quarks in that gauge group have to get some of their mass from the Higgs, right, in order for them to turn on a potential for their axion. So you can write down some model where you introduce some new fields, some new gauge group that has an axion and has some QCD-like potential for it, and then the new fields that are charged into this new gauge group also have to be charged into the standard model weak group, and they have to get some of their mass from the Higgs vacuum expectation value. So you can play this whole game again. Now, instead of having it be QCD that generates the bumps in this potential, it can be someone else's copy of QCD. So I could spend a lot of time talking about how this model works in detail. There are various interesting constraints on it, but I'll save that for the Q&A this afternoon if you're interested. Okay.
Question.
Yeah.
So you said that basically nearby vacua don't change much the value of the vacuum expectation value, but it changes a lot the value of the cosmology.
Yep.
Does that mean that the potential has to be very primitive?
Yeah, so you could imagine fixing the story by, so the tilt was, set by these linear terms, well, it was set by, we imagined G was a breaking of a shift symmetry in this field, and that was the leading piece in that was giving us the tilt. And so you could imagine changing the tilt, making it so low that between vacuum to vacuum, the CC changes by an amount. Okay, but then, so then the size of G, now instead of being set by desire to get the Higgs mass to come out right, it's set by the desire to have the change in the cosmological constant be small. So that is many orders of magnitude smaller. And it turns out that then, if that's what you do, so then your CC changes by a small amount from minimum to minimum, but then you can't write down a theory where you're efficiently scanning the Higgs mass. Okay. Yeah. So yeah, again, it's sort of a game of whack-a-mole, right? If you want to solve the Higgs mass problem, that's okay, but the CC problem kills you. If you want to make it so you're not changing the CC by a large amount, you can't any longer tune the Higgs mass appropriately. Okay. I just want to bring up a sort of dual version of this picture, just to, again, give you a sense in which there are lots of ideas and they're all worth thinking about. So the way this original story of the relaxion worked was there's a field evolving through its potential. There was always dissipation as the field evolved, right? We're imagining the field's evolving during inflation, so there's always friction. And then at a special point in the evolution, some bumps turn on. Okay, so if you always have dissipation, then you pretty much stop as soon as you hit the bumps, right? That was the idea of the original relaxion. But you could imagine, instead of making that your story, you could imagine flipping the roles. So you could imagine saying, what if I have some field that's evolving over some potential, okay, where there's always bumps? So what if there's some potential with some overall tilt, so it's going to be rolling down it, at least it's classically rolling down it, and that potential always has some bumps, so it's some sort of washboard through the whole range of the field. Okay. And if instead of having, so of course, if dissipation were turned on the whole time, then this field would just never go anywhere, right? It would just get hung up on one of these minima and do its thing. But what if the bumps were always there, but dissipation turns on at a special point in this evolution? So then this field would evolve down its bumps, and then there'd be some special point where dissipation turned on, and then the field would stop shortly after the point where dissipation turned on. Okay, that's sort of the dual of this picture, right? The bumps are always there, dissipation turns on at a special point. All right. So that's an interesting idea. So you can ask yourself, well, how do I make that work, right? So in the original story, to always have dissipation, we just imagined this was happening during inflation. To make this story work, we use a second possible source of dissipation in the quantum field theory, which is particle production, right? So if I have a field, if I'm looking at the equations of motion for some evolving field, and it couples to some other fields, it can dump energy into those other fields, into the production of those other fields, right? That's another mechanism that effectively looks like a source of dissipation for a dynamically evolving field in a quantum field theory. So I just want to loosely give you a notion of how that might work. So imagine we had some field that's an axion-like field. It has some axion-like coupling to some massive gauge fields. Right now, I'm not going to specify any relation to the standard model. I just want to illustrate how this works. So imagine it couples to the topological term of some gauge sector, and imagine those gauge bosons are massive. Okay, so now what we want to imagine is this field, this axion-like field, this is the one that's evolving over some potential with bumps in it. And we want to see how this coupling can serve as a source of dissipation that turns on at a particular point in the evolution of the field. Okay, so I can actually look at the massive gauge bosons. I can look at their equations of motion. It turns out I can ignore the equations of motion for the longitudinal component. I can just focus on the transverse polarizations. So if I just look at the equation of motion for the transverse polarizations, okay, it's some normal-looking equation of motion for the gauge field, right? It depends on the mass term. Depends on the mode, and then it depends on this coupling, in particular the coupling to this axion-like field, and it goes like a derivative, a time derivative of that axion-like field because of the nature of this coupling, okay? So that's just the equations of motion for the transverse polarizations of those massive gauge fields. And if you imagine now that phi dot is constant, okay, so neglecting for the time being any sort of back reaction, if phi dot is approximately a constant, then of course we can go ahead and solve these equations of motion to get some normal oscillatory behavior that corresponds to some frequencies, and the frequencies are just set by the mass and the mode and whatever the constant value of phi dot happens to be. Okay. But of course, it's an oscillating solution if these frequencies squared are positive, but if the frequencies are imaginary, so if the frequency squareds are negative, then of course this goes from an oscillatory solution to the equations of motion to an exponentially rising or falling solution to the equations of motion. All right. So the condition for it to be an exponentially growing solution, right, that's just, that amounts to the requirement that these frequencies be imaginary, and that corresponds to just a requirement on, and particularly the term with the minus sign, that the phi dot, the absolute value of phi dot, be larger than some amount that's related. It's the geometric mean of the mass of these gauge bosons and this scale f of the axion-like coupling. Okay. So if phi dot in the field exceeds that product, right, then it's possible to have an exponentially growing solution for this field. And you can ask, where does the energy come from to make an exponentially growing solution for the gauge fields? Well, at the end of the day, if you actually solve the full coupled set of equations of motion, the energy would actually be coming out of the kinetic energy of the field phi itself. It would be coming out of phi dot. Okay. So this is a slightly roundabout way of arguing for it, but hopefully you can at least see qualitatively. If I have this field phi that's evolving down its potential with these bumps, if as it evolves along these bumps, the value of the mass, and it couples to some massive gauge boson, but if its mass is related to the, if the position of phi is related to the mass of the gauge bosons, so the mass of the gauge bosons are scanning as I go along this potential, then at some point, if the mass of the gauge bosons is scanning from larger to smaller, then at some point, this term will become smaller than the kinetic energy stored in phi, and now phi will be able to dissipate energy into particle production of the gauge bosons. Okay, so this would be a way, right, of having some field phi evolving along its potential, having no dissipation over some range of field values, but if the phi is also scanning the mass of these gauge bosons, at some point the mass of the gauge bosons gets small enough that phi can dissipate energy into production of the gauge bosons. So dissipation turns on at a special point, and then phi stops shortly thereafter. All right, so that's a cool idea, right? It's actually straightforward to think about how you could turn that on in the standard model, right? So if you imagined having this axion-like particle coupled to the massive gauge bosons and also coupled to the Higgs mass, right? Now imagine instead of this field, instead of phi scanning the Higgs mass from positive values to negative values, let's imagine phi scans the Higgs mass from very large negative values to positive values, okay? So the Higgs mass squared starts out at very large negative values. The vacuum expectation value of the Higgs is enormous. The mass of the gauge bosons is very large, right? So phi, even if it couples to massive gauge bosons, it's not able to undergo particle production. But as phi rolls down its potential, it's changing the Higgs VEV to smaller and smaller values. The Higgs VEV changing to smaller and smaller values changes the masses of electroweak gauge bosons to smaller and smaller values. And so at some point, the gauge bosons, electroweak gauge bosons, become light enough that this field phi can dissipate energy by producing them, right? And then it stops. So that's a more roundabout way of getting the Higgs mass squared to be small, right? Really what happens is this field phi stops rolling when the masses of electroweak gauge bosons get small enough, when they get close enough to the weak scale. Okay, so that's a different way of running the same story. This way of running the story doesn't require you to do anything crazy about inflation. You're using a different source of dissipation for a dynamically evolving field to do pretty much the same thing. Now, there are other problems and abstractions in this version of the story. It's not really any better than the original version of the Relaxion. All I really hope to convince you of is there are multiple ways to try to make this work. Nobody has found really the perfect solution yet, but these ideas are only 2 years old. So maybe one of you will figure out the right way to make the dynamical evolution of the field pick out the value of the weak scale. All right, so hopefully it's just inspiration to you. All right, so in the last 15 minutes now, I want to get really crazy. Okay, so these last two ideas, so neutral naturalness, that's had about 10 years for people to start working at the details. That's starting to get pretty mature. The Relaxion is about 2 years old. People are thinking about it a lot. There's still a lot of room before the solution really works, but at least people have had some time to think about it. So now I just want to give you some really wild ideas just to try to point your mind in different directions as you think about the hierarchy problem moving forward. So the last example that we had of how to solve the hierarchy problem was to try lowering the cutoff, right? We understood if the cutoff actually of the standard model or if the Higgs were close to the value of the weak scale, then we wouldn't have to worry about UV sensitivity because there's really no UV in the theory, okay? So normally the way that we do that, again, we do that in lots of familiar ways. Maybe we have large extra dimensions in which the gravitons propagate. Maybe we have a warped extra dimension in which gravitational redshift changes fundamental scales as we go across the extra dimension. So that's what Randall-Sundrum models do. So those are all very interesting theories, but one of the problems of any of those theories is, you require some very elaborate construction in some extra dimensions that has to be arranged just so in order for the weak scale to come out right. And all of those constructions predict lots of new particles that are not far in mass from the weak scale, and we haven't seen them, so we're not sure if that's what nature has chosen. All right, so here I just want to point out there's a very interesting way you could try to accomplish the same things that we try to do in very orderly theories of extra dimensions, not by using very ordered constructions in an extra dimension, but actually by borrowing some ideas from condensed matter physics. Okay, so here hopefully, again, this is just an opportunity to expand your mind. So the idea is gravitational Anderson localization. It was a proposal by Ira Rothstein from 2012. I think Giovanni is the only other person in this room who's read that paper. It's a paper that was published in Physical Review Letters, and it has only one citation. Well, it's not because it's obviously wrong, but the proposal itself is complicated enough to actually understand how it might really work, and also people just haven't thought about it enough. So I just want to put it in your minds today so you can go home and think about it, and maybe this will be a fruitful way of stimulating you to think about some new ideas. Okay, so that's a very interesting sounding term. So first, let's remind ourselves of what Anderson localization is, and then we can see what it might have to do with the hierarchy problem. Okay, so what's Anderson localization, right? So Anderson localization, the genesis of Anderson localization, this is something we probably all learned early in our careers when we were studying solid state physics, but then we forgot once we started focusing on high energy physics. So the idea is, what if I just have a one-dimensional wire, right? And I'm interested, say, in the motion of electrons through this one-dimensional wire. Now, of course, if the wire is perfect, then the electrons will just propagate freely down the wire. But generally, of course, these objects have defects, and the defects then might cause some interesting physics to happen to the electrons as they propagate. So what Anderson wanted to do, right, is he asked, okay, let me just write down a toy model for my wire where I just discretize it, right? So I write down a simple one-dimensional lattice for the wire. So instead of taking a wire in one dimension along which the electrons propagate, let me instead make a discrete model that consists of a bunch of different sites that are spaced by some regular amount. Okay? And then let me parameterize the effects of disorder in this wire by imagining that at each site there's some element of disorder, right? So it's giving some potential at each point in this lattice that varies by some amount. So in a real wire, you would think this might just correspond to little actual physical defects in the wire that are scattered at various points along the wire. And an electron that's trying to propagate down the wire will see all of these defects. Okay. So, all right, so Anderson wrote down a Hamiltonian. So generally, you can write down a Hamiltonian for this discretization. So it has various terms in it. So you can label the Hamiltonian by the site. So the site is I, so that corresponds to each one of these. And we imagine there's some sort of impurity that lives at each site, okay? So there can be some energy associated, some potential energy associated with the impurity at every site. So that would give you these terms, right? Those are just the bound state energies of all the impurities. And then also, of course, we want to have some notion of hopping terms that an electron could use to propagate down the wire. So generally, there should be some tunneling terms or some hopping terms that give you matrix elements that cause you to hop from one site to the next. Okay, so those are the hopping terms. All right. Now, in general, of course, so that's the general Hamiltonian you might write down. So Anderson made some simplifying assumptions. He said, okay, in a real wire, there's pretty much, I should imagine there's some more or less uniform hopping terms that will give me motion along the wire. So, and let me assume those hopping terms are nearest neighbor, right? So if I assume the hopping terms are nearest neighbor and are all uniform in size, then I can make some simplifications to these tunneling terms. All right, they just have nearest neighbor form. The other thing that Anderson said is, okay, you know, disorder, I don't want to make any special assumptions about the impurities from site to site. I want to imagine they're just some randomly varying potentials. And so let me just imagine that the strength of each impurity is drawn from some flat distribution randomly in size that varies over some range. Okay, from, in this case, the range of the impurity potentials ranges over values of minus W over 2 to W over 2. Okay, so some random impurities at each site plus some uniform hopping terms. So if you take those simplifications to that Hamiltonian, that's the Hamiltonian that you get for these electrons in terms of the site basis, right? So as you go from site to site, the impurity terms change, right? And then there are these uniform hopping terms that take you from one site to the next. Okay, so that's the tight binding model, right, that Anderson used to understand the effects of disorder in one-dimensional systems. All right, so now it turns out there's a lot of really cool physics associated with the solution to the tight binding model. We don't have nearly enough time to do it justice. But basically what you can do is, you write down the Schrodinger equation for some energy eigenstates, which are just linear combinations of the site eigenstates. And then, actually, if you write down that Schrodinger equation, that actually gives you a recursion relation for the wave functions that are given the overlap between the energy eigenstates and the site eigenstates. Okay, so from the Schrodinger equation for the energy eigenstates for a state of energy capital E, that actually gives you a recursion relationship that gives you the wave functions. Okay? So it turns out you can then study this recursion relationship, and you get lots of interesting effects. So the most famous effect is that in the presence of disorder, in one dimension, in an infinite one-dimensional system, all of the energy eigenstates turn out to be localized. That is to say, they have large overlaps with specific sites, and then they have some exponential fall-off as you go away from some site. So a given energy eigenstate might look like this, where it peaks at a particular site along this wire, and then it has some exponential fall-off relative to the other sites. Okay, so it turns out that all of the energy eigenstates are localized in this way in an infinite one-dimensional system with disorder. That's the famous result from Anderson localization. But if you go from energy eigenstate to energy eigenstate, they don't all have the same. So there's, each one of them has some localization, has some exponential fall-off. There's some width associated with this fall-off that's a localization length. Okay, right. That just corresponds to the fact that all of the wave functions, as a function of our coordinate, have some exponential fall-off at some scale. But one of the interesting results of Anderson localization is that this localization length is not the same for every energy eigenstate. So it changes, right? So some energy eigenstates are more peaked, they're more localized in the wire, others are more spread out, even if all of them have some sort of exponential envelope. Okay, so there are some analytic results for localization in the weak localization limit, or the weak disorder limit, where the hopping terms are much larger than these individual site impurity terms. Okay, so I don't really have time to go into this into detail. Maybe we can get back and do it in the Q&A. Basically what happens is that in the spectrum of energy eigenstates, right, so they range over some value of energies, the localization lengths change as you move through this band. So in the bulk of the band, for most of the energy eigenstates, the localization length is a function of the energy of the eigenstate and of the overall size of the disorder, the variance of the random disorder terms. Okay, so that's a famous result due to Thales that tells you the localization length, or 1 over the localization length, is proportional to the size of the disorder and where exactly you are in the band. And then there's an extra interesting result that actually tells you when you're right near the edges of the energy bands of the allowed solutions, there's actually something that's called anomalous scaling, where the scaling of the localization length with respect to the disorder actually changes. The power law changes. Okay. So that tells you, in fact, states at the edges of the bands are even more localized. They're even more sharply peaked than you would have expected, and they're much more sharply peaked than states that live in the middle of the band. All right. So those are just some interesting results having to do with Anderson localization. And now you're wondering, we just spent the last 5 minutes talking about one-dimensional wires. So what does that possibly have to do with the hierarchy problem? Okay. So here's the notion what it might have to do with the hierarchy problem. So again, this notion owes to Ira Rothstein in a paper that only Giovanni and I have read, but hopefully you will all now go and read too. So I haven't talked much about Randall-Sundrum solutions to the hierarchy problem. The basic idea is you imagine that the universe consists of a slice, some interval, there's an extra dimensional theory with an extra dimension. In that extra dimension, there's a slice of ADS5, okay? And then the Higgs, at least, lives on a 4-dimensional brane on one end of that interval, okay? So what happens in that setup is with the bulk ADS5 and then the Higgs localized at one end, loosely speaking, what happens is curvature localizes the zero mode of the graviton. So there's a 4-dimensional graviton that comes out of this theory that we associate with our graviton, but it's not uniformly distributed in the extra dimension. In particular, it has some exponential profile. And one of the consequences of that is the fundamental scale associated with gravity changes as you move across the extra dimension in exact proportion to the wave function of the graviton. Okay, so if you imagine the highest fundamental scale of your theory, the Planck scale, lives on some 4-dimensional surface on one end of the interval, due to the exponential profile of the graviton, by the time you get to the other end of the 5th dimension, your fundamental scale on that surface has been warped down, corresponding to the exponential profile of the graviton, to a much smaller scale that's exponentially smaller, precisely corresponding to the graviton wave function. Okay. So this is the sense in which Randall-Sundrum models try to solve the hierarchy problem. This is also the sense in which they are somehow dual to technicolor or dimensional transmutation. They take some fundamental scale, they give you an exponentially smaller scale, and in this case, the exponentially smaller scale comes from having a slice of ADS5. Okay. So that's how RS models work. If you haven't thought about Randall-Sundrum models, don't worry about it. If you have, I just want to remind you that's the effective thing that's going on. Okay, so Ira's idea was instead of having some elaborate construction where you have an extra dimension with some interesting warped metric that's solving the hierarchy problem, what if I just had an extra 5th dimension and I put lots of different 4-dimensional branes at various points in that 5th dimension, right? So let's imagine this is the coordinate of the 5th dimension, and let's imagine I scatter branes, 4-dimensional branes, at various points along that 5th dimension. Now, let's just imagine that I vary randomly the positions of the branes, so I put them at random different places in this 5th dimension, and I give them randomly different brane tensions, right? So the 5-dimensional gravity is going to couple to the tension on each brane, and I just imagine I pick a random distribution of tensions of the branes. Okay. So what's nice about this theory is I'm not making any special choices, right? I'm just imagining, the universe has a 5th dimension. There are lots of different 4-dimensional branes that live in that extra dimension. They're just scattered at random places, right? And they have random tensions. So I'm not making any special assumptions to solve any problems. I'm just imagining I have a 5th dimension where the branes are scattered around in the extra dimension, a lot like random impurities in a 1-dimensional wire. Okay? Yes?
What's wrong with making the branes equal distance?
Oh, you actually, yeah. So in fact, in Ira's paper, so he starts out by saying, let's imagine putting the brains at random places, but for simplicity, he imagines if you wanted to write down the tight binding model, there's nothing wrong. You would say, let me in fact just put the brains at a uniform spacing, just like the defects in a tight binding model. And then the only thing I'm going to cause to vary randomly are the brain tensions, right? That would be the analog of varying the defect potentials in the tight binding model. Okay. You could imagine both of them vary randomly. The good news is they could both vary randomly and the conclusions would be the same. But for simplicity, you can assume the brains are at uniform positions and I just vary the tension. Okay. So purely by analogy, right? So purely by analogy, the same sense in which the wave functions of electrons, the energy eigenstates, are localized in a wire with disorder, just by looking, very loosely speaking, at this model for brains in an extra dimension, you expect on similar grounds that all of the, so, you know, I have a 5-dimensional gravitational theory. When I reduce the theory to 4 dimensions, I get lots of different modes that correspond to different excitations of the 5-dimensional graviton. There's going to be a 0 mode, which corresponds to the 4-dimensional graviton that we see. All of those modes will actually end up being exponentially localized in this extra dimension. So each one of them is going to be localized in exact analogy with electron wave functions in a wire. So Ira's argument was that means in particular the graviton 0 mode, the one which we associate with the graviton in 4 dimensions, that's going to be exponentially localized in the extra dimension, right, in exact analogy with Anderson localization. And that means if it's exponentially localized, it has an exponential wave function profile. And so if it's localized and it peaks around some point in the extra dimension, if we, or if the Higgs just happens to live on some brain that is randomly somewhere else in the extra dimension, right, because the graviton has some exponential profile, just like in RS models, the fundamental scale on each of these brains is determined by the exponential profile of the graviton. And so if the Higgs happens to live on some brain that's randomly some other distance from where the graviton is peaked, the fundamental UV scale that it feels of quantum gravity is much lower. Okay. So instead of doing some elaborate construction with picking a special metric in an extra dimension, the idea is, what if you just randomly throw brains in an extra dimension? The graviton should localize in analogy with Anderson localization, and maybe you can explain why the weak scale is so much smaller than the Planck scale. Okay, so there are some technical obstructions to actually making this idea work. Again, I can talk about them more in the Q&A. Mostly what I want to convince you of is there are lots of ideas out there, right? And we haven't devoted nearly as much attention or time to those ideas as we've devoted to supersymmetry and global symmetries. Now, hopefully it's clear to you from this lecture, these other ideas, they're a little crazy, right? They don't always work. They have all sorts of constraints. You have to assume the universe feels, you know, special about you to make all the things work. But, and so I think normally over the last 30 years, the reason why people didn't think about these things is it was much easier just to imagine that supersymmetry or global symmetries were explaining the hierarchy problem. But the fact that we haven't seen any evidence of supersymmetry or global symmetries at the LHC, that should free your mind, right? It should free your mind so that you should think maybe it's time to push in different directions, maybe it's time to come up with new ideas. The ideas aren't always going to be pretty, but if we think about them hard enough, maybe we'll end up with new types of solutions. And then you know, in 10 years, instead of me being here telling you about these crazy ideas, maybe in 10 years, you can tell some new students about the new paradigm for solving the hierarchy problem that you and your colleagues have come up with. Okay, so I had other crazy things I wanted to talk about, but well, I ran out of time, so I'm happy to talk about those in the Q&A if you'd like. There are lots of interesting and cool ideas that are only beginning to be worked out that I think are really fun, but I can tell you about those later. I just want to conclude again with this notion, you know, the hierarchy problem is an interesting problem. It's a speculative problem because it involves not any facts that we've actually measured in the universe, right? There's nothing wrong with the Higgs or the weak scale if the Higgs mass is fine-tuned. The hierarchy problem is really a notion of a disagreement between our expectations of how quantum field theories work and what we see in nature. Okay, so we use the existence of this tension as a strategy to predict new physics, right? This strategy has worked for us well in the past. And so with respect to the Higgs mass, the problem is there in a very sharp form. And so we try to come up with ideas that would explain or solve the hierarchy problem. So we have these traditional sets of ideas that have been very well worked out. I tried to tell you about those last lecture. This lecture, I tried to tell you that, you know, those aren't the only ways of solving the hierarchy problem. maybe there are qualitatively new ways of solving it that we haven't worked out yet. Of course, none of this actually has to happen in nature, right? Maybe nature doesn't care about hierarchies and Higgs masses. That could be perfectly true, and that's fine. But there's something sort of deep and compelling about this picture, and solving the hierarchy problem, it points to lots of interesting new things, right? Maybe it points to analogs of Anderson localization in an extra dimension, or maybe it points to new space-time symmetries, right? So solving the hierarchy problem forces us to extend the standard model in very interesting and fundamentally different ways, and that's why it's fun to think about, but it also gives us new predictions that we can use, we can make, and we can test at colliders and other experiments. Okay, the real take-home message I want to give to you is, to the extent that the hierarchy problem is a problem, all of our old and familiar solutions that we've worked on over the last few decades, they don't seem to be right. So this is now a chance for all of you to come up with new ideas and to test them in the field of experiment. So that's all I wanted to say about the hierarchy problem. My last lecture this afternoon, I want to talk about all of the other interesting ways you might try to extend the standard model at the weak scale or the TeV scale that don't have to do with the hierarchy problem. But again, thanks very much for your time.